Hey everybody, real fun one today. Heading into one of those zero gravity planes. Let's head into the classroom. All right, so if you haven't watched the videos on the zero gravity planes, pause this and go give them a watch. Oh wait. That long enough to wait, you think? Is that long enough to wait? Do I just keep waiting? Or do I just hang out with Alan? Or just hang out with Alan? I guess I can just hang out with Alan while I'm waiting. Great, you're back! So those planes, you're basically getting a sense, and if we look at the three scenarios that are here above, we're getting sort of a little bit of thing going on here with these different locations, and basically we would call them hypergravity and then microgravity. So just to dive a little bit deeper what's going on, we're getting the plane to turn, and as the plane's turning, we're in that like A location is here. We would get a sense that's like a little bit like a squish because the plane is going to push on us and we're going to try to inertia, right? And then at point B, we're actually going to go like, ooh, kind of deal going on because we're going to try to keep going the way we're going and the plane's going to start to descend. In those two regions, this is very, very similar to what we talked about a long time ago in elevator. In the elevator, you get those two feelings, that like squish and that ooh feeling. This is just that to an extreme level. By taking it to that extreme level, because we get that hypergravity sensation, we then also get the microgravity situation. And you watch the one video, they fly in these parabolic arcs and they fly in bigger and bigger and bigger and bigger ones. And when the hypergravity is larger, so is the microgravity more extreme. So if you watch the video, they get the feeling like they're on Mars, and then they get the feeling like they're on the moon, and then they get the feeling as if they're weightless. And they get those different sensations. So if we then think about being inside one of those planes, that would give us an opportunity to have various measurements for little g. You would actually get a couple different opportunities to measure little g. So that's what they're saying is basically if we have those spots where we're getting a couple different spots where we're seeing little g being larger than what it normally is here on Earth, smaller than what it is here on Earth, and then obviously the students could measure just on Earth as well. So you're getting a bunch of different little g values. Now, if we're thinking about this, right, and we start going through the questions here, you would feel heavier than you normally would at A and C. These are like those squishy spots, and you would get that lightness at B. But now they're going to try to do an experiment, and if we're trying to think about what we're controlling for an experiment, we remember that for a pendulum, it's really important to control length because length has a direct connection to the period, so we would not want to change the length. Now, the other thing that is important is the amplitude. Now, technically, amplitude has no effect, so we don't have to keep it constant, but it's good science to keep it constant. However, it is important to remember that amplitude has no effect for small angles. So we would want to keep it an angle of, for instance, 7 degrees or 10 degrees, and that would be a pretty important thing. And then as we look at what's asking, we're saying that the students need a method that is real quick, and specifically it talks about minimizing experimental uncertainty. Now, the big thing for the students is they wouldn't have the same opportunity that you had in a digital experiment. They're going to have to use a stopwatch. And because they're using a stopwatch, it's difficult to just time one single period, especially when it's going to be probably in that 1 to 2 second range. So the easiest thing for them to do to decrease experimental uncertainty would in fact be to measure 10 cycles and then divide by 10 to get the period for just one single cycle. That would be the easiest way to do that. Beyond that, it's pretty much the pendulum lab that we had done. So up until that point, that's really what it is. Now, in parts D and E, they're asking us to do a little bit of analysis, making the assumption that the students did, in fact, collect data. So we're saying the kids collected the data, and here's the graph that they have, And if they have this on the y-axis, what's on the other axis, and what's going on with all this? D and E are actually pretty challenging to answer without having done the data collection. But there's a trick we have. We've learned a whole lot about something that has been beneficial for sure when we've needed it, but it's more powerful than you understand. It's more powerful than you know at the moment. And that thing is called linearization. Linearization holds tremendous power in data analysis, but it also holds tremendous power when we think about it working the other way. So we're going to discuss something known as backwards linearization today. And when we think about backwards linearization, if you think about the process of linearization, it's the same process but backwards. So if you think about the steps we typically did, yeah, we collected the data, but we have a graph, right? Once we have the graph, we identify the shape, right? Modify the data, right? Check our square, right? That's our basic process, and then we get our mathematical model. That's pretty much what we're doing, right, every single time. Now that backwards would be to have the model and then think what we would have done to that. Now, since this is a pendulum, it's pretty easy for us to actually just think about the equation for a pendulum. So if we think about what's going on, we would say that the period of a pendulum would be 2 pi radical L over G. Now, if you remember, this version is fine, but I would prefer if this was the square, guys. I'm going to square both sides of this. So I would get TP squared, and this would be 2 squared, which is 4, pi squared, which is pi squared, and then L over G. This is just the equation. But now if I think about this, backwards linearization works very simply like this. I want to separate out what the students are graphing, separate out the variables, and everything else would have to be constant. And because it has to be constant, that means, in fact, that it would have to be in my slope. So if you think about the experiment that the students would perform, well, TP, that's going to be changing, and that's fine. That's on one side of my equation. But I want to now look on this side and think about each one of those things and think about what would change in the experiment and what would not change in the experiment. Well, 4, that's a number. So if that changes, we got way bigger issues. Pi squared is a value as well, so that should remain constant. Length, the length should remain constant. The length should stay constant because that's one of the things that we would hold constant in our experiment. And little g would be the variable. So if I rearrange this a little bit, if I just write this a little bit differently, we would get that TP squared be 4 pi squared times L times 1 over G. I'm going to put all of this in parentheses, put all of that in parentheses. And what we end up with, and this is where it gets really, really special to us. This is where it really starts to matter a whole lot. We would have that TP squared 4 pi squared times L 1 over G. And this is where the backwards linearization starts to shine, because we think about y equals mx plus b. Well, there is no intercept to worry about, so I'm not going to worry about that at all. But that means that this would be on the y-axis of my graph. This would be the slope, and then this would be the x-axis of my graph. So if I were to produce a linear graph, it would be TP squared. It would be 1 over G. This would, in fact, be linear, and the slope of this graph would be equal to 4 pi squared L. So if we look, I'm literally using the equation and thinking about linearization and thinking about how this is functioning to understand what a graph would look like for students. Now, what's interesting is we can take this one step further. I don't need to for this question, but I need to for, it's in my heart. I can't not. Us looking at this, we know this is a double linearization. This has to be a double linearization. And I know that because we would have TP and G. That would be the data that the students would have collected, TP and G. The period and the acceleration due to gravity. That would have been their data. So I know that this is a double linearization. So by looking at this equation, I know exactly what the slope is. I know exactly the fact that this is a double linearization, and I can figure out what that original graph would be. Now, in the question, they ask if they have TP squared on the y-axis, what has to be on the x-axis for a linear graph for a straight line? Well, it's 1 over g. Then they also ask, they say for them, the slope of that graph is 9.8 meters. Well, we just said that 4 pi squared L would be equal to the slope, which would be equal to 9.8 meters. So I could divide both sides by 4 pi squared. Cancel out. And I'll be able to figure out the exact length of that student's pendulum. So from very little information, I can figure out exactly what the graphs look like originally, exactly what the students used as a length of a pendulum, and we don't know. We have no idea. Right? It's not a thing that was told to us. It wasn't set in the problem anywhere. 1 kilogram sphere, sure knew that, but nothing else. So I get all of this power. Just to be interesting, what I actually did was I actually collected this data using the pendulum lab, and you could too. And let's take a look at that data. All right, diving into the data. So what I did was I took the pendulum lab and I changed little g to different values. I just used nice round numbers here. It doesn't really matter. You could use whatever you want. But you can see this first graph that I'm getting. This is very clearly that inverse shape graph, right? Very clearly that inverse shape. So naturally, I would invert the values. That means I would inverse little g. So then I got this nice, beautiful graph here, and you can see that nice side opening parabola shape, which means I have to square the period. And then finally, I get this beautiful linear graph. And then just for fun, if you take this, what I did was I took the slope, that the slope of this graph is this 27.7. You take that and divide it by 4 pi squared. What you end up with is 0.7 meters, and that's exactly how long I had set the length in the applet. So it's a fun little thing if you want to try it out for yourself, to prove it to yourself that it exists, to prove that it's real. If we go back and we look at this experiment, interesting experiment because this ties together linearization, data analysis, right? It ties together understanding lab procedures and lab equipment. It also ties together technically, if we go all the way back to elevator, right? The elevator stuff that we did a long time ago. This is one heck of a question. It's all sort of beautifully mixed into one. Now, for those of you that are curious more about backwards linearization, I would be too, because it is the type of thing that can be an amazing skill to put into your back pocket to pull out when you need it. There is an entire video on backwards linearization that I'll link you to. Until next time, see you in the next one.